On July 30, 2026, IBM and a coalition of research partners released 3 simultaneous papers declaring a new milestone: trusted quantum advantage. This claim follows a decade of debate sparked by Google's 2019 announcement of quantum supremacy. Within days of Google publishing that their 53-qubit Sycamore chip completed a calculation in 200 seconds that would take a supercomputer 10,000 years, IBM issued a rebuttal. They proved their Summit supercomputer at Oak Ridge could simulate the exact same circuit in 2.5 days. The 2019 benchmark relied on random circuit sampling. It was a contrived task that generated one-off bit strings, making it difficult to verify. As classical algorithms improved over the next few years, supercomputers eventually matched the quantum outputs. Useful quantum computing depends on the ability to trust the hardware's output once a system solves a problem beyond the reach of classical verification. That specific hurdle defines the central bottleneck of the noisy intermediate-scale quantum, or NISQ era, the verification paradox. This chart maps the paradox. As quantum computational power increases, it crosses the vertical limit of state-of-the-art supercomputers like Frontier or Fugaku. Once the computation enters this shaded mathematical blind spot, supercomputers can no longer verify the answer. Previous claims navigated this dark zone by extrapolating data from smaller circuits, effectively a proxy of a proxy. IBM's July 2026 announcement introduces 3 distinct rigorous methodologies to solve this problem, providing frameworks to mathematically verify correct answers without a classical safety net. The July 2026 papers focus on bridging this gap, testing 3 methods to validate quantum results as they move past the classical frontier. IBM has established a strict, rigid 2-part condition for declaring quantum advantage. The hardware must outperform classical methods in speed, cost, or accuracy, and the result must be rigorously validated. The first of the 3 papers, co-authored by the University of Chicago and IBM, approaches this by building validation directly into the circuit itself. Look at this base layout. The researchers constructed a 70-qubit, depth 70 Clifford circuit. Into that easily simulatable structure, they injected 468 non-Clifford T-gates, significantly increasing the complexity of the calculation. They encoded this setup across 97 physical qubits on the Heron processor, utilizing what are known as space-time codes to manage the information. By applying error detection post-selection, the researchers filtered out faulty runs based on specific error syndromes. This mechanism reduced the effective gate error by a factor of 10. The hardware yielded a mathematically self-certifying fidelity lower bound of 0.284, measured at a 95% confidence interval. Because of the precise mathematical structure of the space-time codes, the circuit verifies its own reliability through intrinsic math, eliminating the need for a supercomputer to check it. The second paper, produced by Kedma, Riken, and Bluequbit, moves away from pure mathematical proofs and tackles physically motivated materials simulation. The target was a highly complex physics problem, resolving long-lived subharmonic oscillations within a 2-dimensional Floquet-Ising model. To establish a baseline, the team ran state-of-the-art tensor network simulations on NVIDIA H100s and Pauli-path simulations on Japan's Fugaku supercomputer. Up to 35 qubits, the classical machines and the quantum hardware matched. This graph tracks that exact classical boundary. Right around 51 qubits, the tensor networks and supercomputing methods reached their limit and broke down. Using QEDMA's QESM error mitigation software, the IBM Heron processor extended the simulation past the 51-qubit mark, reaching 74 qubits. Because Fugaku could no longer check the math at 74 qubits, the researchers had to identify a different verification method. Their solution was to run the exact same calculation on a completely different architecture. They verified the outputs against Quantinium's H2 and Helios trapped ion machines, confirming the results matched. Cross-platform validation between superconducting and trapped ion systems proves the physics is real, bypassing the classical supercomputer bottleneck entirely. The final paper, from Algorithmic and IBM, shifts the verification strategy away from both internal math and external hardware, focusing on process-level validation. Their goal was to compute a new observable called the operator-Loschmidt echo on 56-qubit Heron circuits, a task requiring roughly 1,000 2-qubit gates. At this scale, leading classical simulation methods began to diverge. 3 separate simulation groups ran the problem, and all 3 disagreed with each other and with the quantum hardware. This diagram illustrates algorithmic's workaround. They ran the exact calculation across 5 different quantum processors, each possessing a distinct physical noise profile. By feeding these environmental variables through the calculation, researchers validated the underlying noise model instead of relying on a classical baseline. When answers cannot be checked by external math, proving the validity of the noise process provides a way to trust the result. To prevent another round of disputes, IBM submitted all 3 of these results to the open-source Quantum Advantage Tracker, inviting the global community to stress test the classical benchmarks. All 3 papers were released as preprints pending peer review. More importantly, the authors of the physics simulations stopped short of formally claiming advantage in their own texts. They exercise caution because of a historical pattern known as dequantization. The Kedna and algorithmic results rest on heuristic error mitigation, not fault-tolerant computing. Historically, whenever quantum researchers use heuristics to secure a lead, engineers develop better classical algorithms to match those claims within 18 months. Trusted advantage in 2026 is an ongoing leapfrogging arms race, not a final victory over classical supercomputers. For R&D leaders in material science or chemistry, these validated results provide a practical basis for starting exploratory physics simulations via the cloud. For cybersecurity teams, this announcement does not threaten RSA or ECC encryption. This split timeline shows why. These papers demonstrate physics simulations, not Shor's algorithm. No cryptographically relevant quantum computer exists today, and the migration to NIST post-quantum cryptography standards remains unchanged. IBM's actual commercial roadmap targets 2029 for utility, relying on their upcoming Starling architecture to deliver fault-tolerant logical qubits. The July 2026 papers prove that researchers can verify quantum answers past the classical frontier, a necessary scientific leap that serves as the prerequisite for commercial utility at the end of the decade.